and has served as the dean for that department. He has been a fellow of Indian Academy of Science, has received Shanti Swarup Bhatnagar Award for his contributions, and as I said, a very well-known figure in the field of computer science. On a more personal note, he is one of the best teachers I had the privilege to learn from. I'm really, really looking forward to this talk. Thanks, Jaikumar, for accepting our invitation. Over to you.
Thank you, Rajat. Let me share my screen. Yeah, maybe before that, so I understand that many of you are familiar with this field, but I'm basically going to assume that I'm giving this talk 20 years ago, and which I did at IIT Kanpur on the invitation of Manindra and Professor Ganguly, Shumir Ganguly. And so that was 20 years ago, and roughly the talk is the same. Okay, so but if this will be a computer scientist trying to say physics things and just in a consistent way, so you will realize that again and again you will have to tolerate the sort of computer science statements I make, but hopefully you will be able to adjust them and fit them into your understanding of the underlying physics. I will be hardly talking about any physics, but still it's all inspired by physics, and I won't be talking about these things if the physics did not exist. Okay, so let me share my screen and we'll see. Please ask questions whenever you want, and there is no set agenda that, or a syllabus that needs to be completed. So I hope my screen is visible.
Yeah, so, you can make it full screen maybe if that is convenient.
So I think it's picked up the wrong thing or what? Okay, anyway, let me just make it full screen and I hope it all works out. Yeah. Is that okay?
Excellent, excellent,
yeah,
excellent.
Yes,
yeah.
yes, good. Yeah. So from classical to quantum computation. So my plan is to sort of explain things, explain something about computer science in the beginning, and then we will talk about other things. Okay. Yeah. So the first part will be actually the classical to quantum, and the second part is I would like to tell you about this thing called quantum teleportation, which you probably have heard of and some of you know, but I would like to somehow say it in a way in which it makes sense to a computer scientist. So in computer science, we use something called classical one-time pad for, I'm sorry. Can you see things still? Or?
Yes, yes, we can see, yes.
Yeah. Okay. So, yeah. So there's something called one-time pad, which is used for communicating things secretly. And the idea is to use the same sort of logic. And somehow when we use the same logic in quantum computing, it turns into quantum teleportation. It won't exactly work out that way, but let us see how far our classical comfort with the one-time pad allows us to imagine that quantum teleportation should also be a natural thing. Okay, so let's go on. Yeah. So I will tell you about classical computation, classical deterministic reversible computation, classical randomized computation, classical probability, but I'm going to do classical probability in some sort of complicated notation. And hopefully that will help us with the quantum notation itself, and quantum circuits, quantum measurements, all in a very basic, simple way, only for the purpose of completing my talk. Yeah, it will not be a complete treatment of the subject. Okay. So in computer science, the sort of courses that Rajat would teach, you would like to say, understand what do we mean by a computational problem? When do we say that the computational problem has been solved? And when do we say that the solution is correct? And when do we say that the solution is efficient? Okay, so these are questions which are part of theoretical computer science. And I would like to give you some basic idea of how these questions are modeled in theoretical computer science. And later on, we will try to apply the same sort of thinking in the quantum context. So a problem consists of inputs and outputs. Yeah? So the input is a sequence of symbols. And by now, everybody is comfortable that inputs will be sequences of zeros and ones. And the output for now, for today, will be just a yes, no answer. Okay, so you have to say whether it is something is yes or no. And for example, so here is this thing that we call graph. Yeah, so it's a graph which has 4 nodes, and there are these 4 links, and the input could be this. Now, this doesn't quite fit into this part. I mean, unless yeah, you think a little more deeply. So, and then the question that we might ask about this graph is there a path from node 1 to node 4? Okay. So in this graph, of course, there is a path from node 1 to node 4. So in general, how would this be actually modeled when we do theoretical computer science? We'll have to specify how the input is specified. So we will say, oh, the input is specified in the form of a matrix. That is, we have 4 rows and 4 columns, 1 for each of these nodes, and we put a 1 if there is an edge. Yes, so there is an edge between 1 and 2, so there is this 1. And there is an edge between 1 and 3, so there is this 1. And you have this matrix. But if you want, you could turn this matrix into one long sequence. Yeah? You could put one row after another, and you get this sequence. Okay. So now, when we say that we have a computational problem, what we mean is that somebody is going to give us this sequence. Yeah? This sequence of 16 bits. And looking at this sequence of 16 bits, you have to tell me whether there is a path from vertex 1 to vertex 4 in this graph, in the graph represented by this input. So that is how typically one models computational problems in theoretical computer science. Okay. And the final answer will be yes or no. So you have to say 0 or 1. And 0 means no, 1 means yes. Okay. So now we understand what a problem is and what input-output behavior the problem demands. Now, the question is, the input-output behavior has been told to us. The question is, how do you realize this behavior? So you are supposed to take the input and perform some operations on the input so that the output shows up, yeah, shows up in memory somewhere. Okay. So the questions to ask is, what basic operations are we allowed to perform on the data to convert the input to the output? When will this solution be considered efficient? Yeah. And efficient with respect to what? Yeah. So often, I think most of us would want our programs to run fast. So we would say efficiency means you must take a small amount of time. But there may be situations, especially in modern times, when processors, they are small, they want to consume less amount of energy, they don't want to be bulky, and they want to carry a lot of space. So having algorithms which use limited space might be of importance. Or access to input might be important. That is, you might be implementing an algorithm meant for a router, in which case inputs are not going to be stored. The input will just, you'll only have a small amount of time to look at the input before it just goes off your window. Yeah? So access to the input, whether you're able to scan back and forth in the input, those are questions. And for each of them, computer scientists invent models and try to invent solutions in that model so that they can finally be implemented with restrictions whenever there are restrictions. Okay. And the other key question, which will be important for our discussion today, is, do we allow randomization? Okay. Now, what does randomization mean? I'm sure you have some idea of what randomization means. We will try to make it precise very soon. And if we allow randomization, are we allowed to make some error? That is, if the input is yes, are we allowed to say no? And with what probability are we allowed to say no if the input is actually yes? And similarly, if the input is no, what's the probability that we say yes? Which should be a small probability. Yeah. So those are typically involved in the discussion of efficient solutions in any computational model. Okay. Now, so let me get a little more concrete. All this is abstract, just to give you an introduction of what a theoretical computer scientist does or worries about. For us today, the model of computation will be quantum circuits. Okay. So now the two basic starting points, inputs and outputs. Okay. So it's, everybody understands that a circuit transforms inputs to outputs, and we will assume that there is a fixed set of gates like NOT gates, OR gates, AND gates. These are the only things that we will allow. And with these gates, we want to implement the transformation that we want. That is, maybe the data corresponding to the graph will be put here, and you have to decide on the output whether vertex 1 is connected to vertex 4 or not. Okay, so design a circuit for that. Now, when you try to design the circuit, you will need a certain number of gates. And it's natural to say we will consider the solution. So notice that the solution is not the output. I mean, that usually when we are told to solve a problem in a mathematics textbook, the output that we write in our notebook or the exam sheet is the solution. Here, solution itself is an algorithm. The problem is the problem of taking a graph and determining whether the vertex 1 is connected to vertex 4 or not. The solution to the problem is a circuit. It should be general purpose. No matter which graph you feed, it should be able to determine whether vertex 1 is connected to vertex 4 in that graph. Okay. So when will this solution be considered efficient? If it involves only a small number of basic gates. Okay. And it turns out that, for example, these gates AND, OR, and NOT, AND and OR are not actually reversible gates. First of all, for a reversible gate, the number of inputs should be equal to the number of outputs, because the number of possibilities for the input is 2 to the power number of wires coming in. And if your output has fewer wires, then there is no way there can be a one-to-one mapping from the input to the output. So reversibility will not be possible. But it turns out, and it's not that important for us today, that all classical computation using AND, OR, and NOT can actually be made reversible. Okay, so there is a different gate. Instead of using AND, OR, and NOT, you can use one special 3-input gate, yeah, or a 3-register gate. I'll tell you why I'm calling it a 3-register gate later. So a 3-register gate called a Toffoli gate, and using that gate, all computation can be implemented reversibly. Okay, yeah. For example, a NOT gate is already reversible. No? If you take an input, apply a NOT gate, you get something. You apply the NOT gate again, you will get the input back. Okay, so NOT was not the problem. The problem was AND and OR, and there is a way, very soon you will see, of implementing AND and OR also in a reversible way by adding some extra bits and embedding this so-called non-reversible computation inside a bigger reversible computation. But the bigness of the bigger computation is not, too bad, just a small factor bigger than the original thing. Okay. Yeah. So this is how we model solutions. And now you might be wondering, this is not what you think of computer science as, or at least a solution for a computer science problem. You think of the solution as to a computer science problem as an algorithm, and an algorithm is written in a programming language. Okay, and that doesn't quite match this model of computation. But if you think a little bit more, what does the algorithm do? Yeah, so inside your computer there is hardware, and there is input, which is in some initial state. Maybe the original graph has been stored. In the first step, the algorithm will operate in one clock cycle and store the data back in the memory or in the logic units or the memory on the on the motherboard. Yeah. And in the next step, again, some hardware will operate on it. It is basically the same hardware, and the data will again be changed. So if you string together, so we use the same, reuse the same hardware again and again and again. But if you did not do that, then what you would see is this big computation consisting of gates after gates after gates after gates. It is true that the same gate is being written again, but you can imagine that the size, the number of gates that you use here will grow if the algorithm is slow. And if the algorithm is fast, then you will not have many layers and this circuit will be small. So this translation between our familiar algorithms in various programming languages and the circuit model that I just described is rather tight, and somehow to analyze things combinatorially, it is easier to work with the circuit model. So please don't be alarmed if my idea of a solution to a computational problem is different from what you're used to thinking. Okay. So this is all I'm going to say about solutions to problems. Now, today, it will not be very important for me to talk about when a solution should be considered efficient. What we would like to say today is just this: we would like solutions which use the fewest gates possible. Okay? So the whole purpose of complexity theory or efficient computation is to find a way of translating the input to the desired output with the fewest gates. Okay? And the great promise of quantum computing is that there are problems where the number of gates needed, classical gates needed to perform a certain operation, is much larger than the number of quantum gates needed to perform the same operation. There seems to be no physics limitation to the implementation of those quantum gates. So perhaps there are, for some problems, quantum solutions might be faster than classical solutions. So that is the rough spirit of quantum computation. Today, we will not be getting into solutions of problems and what sort of problems can be speeded up using quantum gates, but we will just try to understand why is it that quantum sometimes does things that classical is unable to do. Yeah. Okay. So this was, so far whatever I said was for classical deterministic computation. And let me quickly tell you how we model randomized computation. A randomized computation is also modeled using a circuit, except that there are some special gates that are allowed. Okay? And I'm going to call them dollar gates. Dollar gates just to signify that you toss a coin to determine the output. Whether the input is 0 or 1 here, the output is always going to be random. That is, it's going to take the value 0 and 1 with probability half. And if you the dollar gates, they take the value 0 or 1 independently. Yeah. And now, even if your input was deterministic, you fed the data about a graph, which vertex is connected to which and which vertex is not connected to which. Here, the output can be random. And it might take 0 or 1 with various probabilities. And how do probabilities arise? The probabilities arise because these are firing and resulting in values here, which are not deterministic. They could be 0 or 1. So you could then start talking about what's the probability that the output is 0 and what's the probability that the output is 1. Okay. But typically, what we require in complexity theory is that for a solution to be good, your output of the circuit should match the output of the problem, the required output, with probability at least say 3/4. And if you want 99% correctness, there are ways in which this error probability can be reduced by repeating the algorithm and doing some tricks. Okay, so don't worry too much. This is what our understanding of a randomized computation is. Okay. And for many problems, it turns out that randomized solutions are known, for which efficient deterministic solutions are not known. And randomization is a very important resource in areas like cryptography, and we will see an example of that very soon. Okay. So, yeah, so certainly I'm going to change the level of the talk. So this is a good time to ask some questions. It's always a good time, but particularly now. Yeah. So if there are questions, I would like you to ask me now. Yeah. Okay. All right. So let me go on, and please ask me if something is not clear. Yeah. So you see, I said that we will have circuits. What are those gates operating on? Gates are operating on memory. Now, today, those little memory cells that you have inside your computer, we are going to use the name register for them. Yeah. So we will call those computers, those memory cells, registers. Okay. And a random bit. Yeah. So a register, suppose, is a random bit. It contains a random bit. So it contains the value 0 with a certain probability and the value 1 with a certain probability. So we are going to say that the register is in state pi. Now, pi is a probability distribution over values 0 and 1. Now, for today, I'm just going to decorate it in this way. So there is a vertical bar here and 2 brackets. Okay. So please don't take this very seriously. I'm just writing this instead of this. Okay. And I'm putting 2 brackets. So some of you who are already used to quantum notation are probably used to seeing just one angled bracket here. I'm putting 2 just to remind ourselves that we are still talking about classical computing. Yeah. But we are trying to use some sort of quantum notation. Okay. Let me see if this works. I'm going to spend 5 minutes trying to say simple things in complicated ways, and I hope it will still make sense. Okay. So if you have a register and it has the value 0, yeah, that means with 100% probability it is 0. There is no question of it being 1. Then the distribution is 1 and 0, because this first position is reserved for 0, and then this position is reserved for 1. Okay. And the state we call 0. Yes. So it's this can be a little confusing. We write a 0 here. This 0 means that the register is in state 0. That is 100% probability here. And when we write 1, that means 100% probability lives in the coordinate corresponding to 1. Okay. And now, if you are this state, you can think of this state as a combination of these 2 states with the corresponding probabilities. Okay. Yeah. So what are randomized states? A random state is a vector of this kind, which has some value in the first coordinate, some value in the second coordinate. Both are non-negative and they add up to 1. Okay. So in 2 dimensions, yeah, they live on this little line segment. A randomized state lives on this line segment connecting the point 1, 0 to the point 0, 1. That's where a state lives. Any point in this line corresponds to a randomized state. Okay. Similarly, when describing the state of n registers, if you have n registers, how many possible configurations can those n registers be in? Okay. The register could be in the state all zeros, or all zeros and 1, all 1 0, and it is in the state 1 1. And if it is a pool of random registers, they might be correlated in some way. So in general, these random registers are in some state. And the state now will have 2 to the n components And each component will be a probability. So nothing has happened. Whatever we used to do for states, we are now and we are continuing to use double brackets to remind us that we are working with randomized computation, classical randomized computation. Yeah, we'll come to quantum computation very soon. Okay, so now in randomized computation, what happens to the state of the register? So you were in some, the registers were in some state, and then you applied some operation. Those registers will again come into some state. Okay, and so each step of a randomized computer with n registers changes the state from one of those 2 to the n configurations to another one of the 2 to the n configurations. Okay, and you can write down a matrix saying that if it was in this state, then in the next time moment, it will be in this state with this probability, this state with this probability, this state with this probability, and so on. Okay. Similarly, for the next state, you write down the various probabilities and so on. So what you get in the end to describe a random operation, you get a 2 to the n cross 2 to the n stochastic matrix. And what do I mean by a stochastic matrix? The columns all add up to 1. Okay. So now I mentioned the Toffoli gate. Let me just actually skip the Toffoli gate. We won't be needing it. But you remember the dollar gate? Yeah, the dollar gate, no matter what the input is, the output was supposed to be 0 or 1 with equal probability. So what matrix does the dollar gate correspond to? Okay, so first of all, what should be the dimension of the matrix? Okay, so a dollar gate acts on a bit. That means it is working on 2 states, 0 and 1. And no matter what the input state is, the output state is equally likely to be 0 or 1. So that's why you have this matrix. Okay. Now, so in probability theory, there are 2 things that we talk about. Yeah. One is the probability distribution itself, which we have now modeled as vectors. The other thing that we talk about are events. Okay, that is, looking at a probability vector, we want to know whether a particular event has happened. So suppose you have 2 registers, and you could ask, are the 2 registers in the same state? Are they equal? Okay, in which case we model the event by this so-called row vector, which says, yes, if your value is 0, 0, then the event has happened. If the value is 1, 1, then the event has happened. If the value is 0, 1 or 1, 0, the event hasn't happened. Now, every event is a subset of possibilities. You know? So if you have a probabilistic event with various possibilities, some of those possibilities, sorry, a probabilistic experiment with various possibilities, some of those possibilities correspond to the event happening. Some of those possibilities correspond to the event not happening. So wherever the event happens, under those columns, you write a 1. Wherever the event has not happened, for those configurations, you write a 0. And now, if you're in a state and you want to know what is the probability, yeah, that a particular event happens, well, if the state was this, and I wanted to know what's the probability that the 2 registers have equal value, well, the equal value happens for, in this case and this case, so the probability should have been 0.7, 0.4 plus 0.7, and you'll realize that the probability that this event happens in this state is just the product of this row vector and this column vector. Okay. So my whole point is that randomized computation can also be viewed as evolution of column vectors under the operation of stochastic matrices. And when you are called upon to determine whether an event has happened or not, all you need to do is to take the current state and multiply it with the characteristic vector. This is called the characteristic vector of the event. characteristic vector, meaning you put ones in the right places. Okay. Now, all right, so I have 25 minutes, I think. How much time do I have?
Yeah, I think that's fine.
Yeah. So, so I will try and so keep whatever I've said about randomized computation in mind. And I would now like to tell you about what this fuss about quantum computing is. Okay. Yeah. Now, it turns out that there are physical phenomena that behave not quite like probabilities. Okay, so here's what happens, for example. So you send a photon through what's called a beam splitter, and it sends either the photon this way or this way. And how do we know that it sends this way or that way? Well, if we put little sensors here, we always find that either this one fires or this one fires. It's never the case that both of them fire. It's never the case that both of them fire with half the intensity or so, something like that. If you send single photons, it's either this one that is detected or this one that is detected. Okay. And then if you send a photon like this, and there is a detector, this detector will finally, this splitter will finally send the photon here or here, and it will be detected either here or here. Now, so we have this very strange situation with us, where what happens is that if you block this, if you block this, then photons seem to show up here or here with equal probability. If you block this, you stop the photons from going this way. The beam splitter might send it this way, but it gets blocked here. Okay. Still, the photon shows up here or here with equal probability. Now, imagine that this was a classical probabilistic system. So you could say, okay, when it comes here, there is some physical phenomenon here, which pushes it this way or this way with equal probability. It's not hard to imagine. But if you keep this on, it shows up in both places with equal probability. When you keep this on, it shows up with both places with equal probability. But when you keep both of them on, for some reason, it shows up only in one place. This cannot happen in classical probability. If some initial distribution, initial state vector, after some number of operations leads to a certain observation, and some other thing also leads to that observation, then their combination cannot cancel things out. There is no negative probability. Okay, so if things can happen in one case and things can happen in the other case, then things must happen in a convex combination of those cases. If you take the average of those two cases, still the thing must happen. Okay. Now, I mean, we can keep arguing that it must happen and it must happen, but it does not happen. Okay. So it turns out that these photons, etc., cannot be modeled using our standard way of thinking about probability. So how do we model this and how does it work? So physicists have taught us how we should model this. So I'm going to just go ahead in a naive way and try to tell you the correspondence. That is, basically, this is my way of coming to terms with quantum probability. Okay. So in classical computing, I used to think of the state of a bit as a P0, P1, and maybe I used to put a square bracket so that I reminded myself that this is classical probability. A quantum bit, so it can be a photon, and maybe it is the polarization of the photon. Let us not worry too much about the previous picture. I'm not trying to correlate what is in this slide with the previous picture exactly, but you can do that. Maybe emerging out of the top here corresponds to 0, and emerging out of this corresponds to 1. But let's not worry about it. Let's just do the math. Okay. So again, qubits, the quantum version of bits, can be in two states, just like this. Okay. But for some reason, and right now this will just look like some fetish, that we use some two numbers whose squares add up to 1. Okay. Means I said that classical states reside on that little line between the point 1, 0 and 0, 1. Yeah, a classical state consists of two components that add up to 1 if you think of these equations. Yeah. Quantum states live on the circle. Okay. It turns out that alpha and beta can be complex numbers, but we won't need complex numbers today. So let's just do real numbers. So a quantum state, the state of a single qubit, lives in this two-dimensional picture on this circle instead of on the line. Okay. When you have n bits, you used to have a vector with 2 to the n components. No difference at all. If you have n bits, you still have a vector with 2 to the n components. We write it with these circular brackets, parentheses, but it is a unit vector. It is a unit vector because the sum of the squares of all the 2 to the n entries add up to 1. Now, what did these numbers mean? They meant the probability of seeing a 0 and the probability of seeing a 1. In quantum, the corresponding quantities are called amplitudes. And they correspond to not quite probabilities, but sort of square root of the probabilities. If you square them, then you will get the probability. Okay. So actually, so far, it looks like there was classical probability and physicists just decided to put square roots on them and call them amplitudes. Yeah. The only thing is that these numbers are allowed to be negative, but the moment you talk about events, whether events have happened or not, you are going to square these numbers anyway and add them up. So I've still not told you what the fuss is about. The fuss comes in as to what operations are you allowed to perform. Okay. It turns out that you are allowed to multiply these vectors with matrices. But these matrices must preserve the length of the vectors in the Euclidean sense. That is, the sum of the squares of the entries should be 1. Okay. But in the course of these operations, the matrices themselves can have positive and negative entries. And in fact, as I told you, the state vectors themselves have positive and negative entries. So when you perform the very same operations, please take the word same with some pinch of salt. Of course, the physical realization in a lab will be different, but the same mathematically similar operations, then cancellation of amplitudes can happen. Whereas in probability, any such cancellation never happened. It was always accumulation. Okay. And to a computer scientist, this sort of cancellation, etc., just becomes too complicated to think about. And it's actually a nuisance. And unless somebody points out that there is an advantage to cancellation so that some problems can be solved faster if you allow cancellations, it's not so attractive. It may be useful for the physicists. It turns out that by allowing cancellations, see, when you're trying to get the input to an output, you can either say that I want a desired output, or you can say, I want to eliminate the undesirable outputs. And the fact that you can cancel things allows you to have the undesirable outputs hang around in intermediate computation. But by the time you get to the end, the amplitudes collide with each other and annihilate each other so that only the good desirable outputs stay in the picture. Okay, so that is roughly a vague way of saying how quantum works. Okay. Now, let me just tell you about a few quantum operations. So there was this dollar gate. Okay, let me pause. I would like you in the next 15 minutes to sort of believe that quantum is not that much different from random. Okay, and then we will see in what ways it is different. So first of all, in random, there was a dollar gate. Okay. In quantum, all gates are reversible. Now notice that a dollar gate is not a reversible gate because no matter what the input was, it replaces it with a random value. Okay, so it overwrites the input with a random value. So there is no way for you to recover the input. Okay. But in quantum, there is this so-called Hadamard gate, which serves as our dollar gate. So there will be no dollar gates in quantum computing. There will be a Hadamard gate. And what will this Hadamard gate do? This Hadamard gate when it is fed 0, it produces an equal superposition of 0 and 1. And when you feed it a 1, it produces an equal superposition of 0 and 1, except that there is this sign. But if you were to observe the register here, you will get 0 with probability half. Why half? It's the square of this number. And you will get 1 with probability half. In this case also, you will get 0 with probability half and 1 with probability half. Okay? But if you do the calculation, if you apply the Hadamard matrix to itself again, this 0 will be restored to 0 and this 1 will be restored to 1. Okay? So it acts like a coin toss, but it's its own inverse, but it has some powerful features which we will soon see. Okay? And there is the other gate that I will need, which is called the control NOT gate. And what does this control NOT gate do? If the first register contains a 0, it doesn't do anything to the second register. So that's why there is an identity matrix here. How should you read this? If the input is 0, 0, the output will stay 0, 0. If the input is 0, 1, the output will stay 0, 1. So there is a diagonal 1, 1 here. However, if this input is 1, then the second bit will get reversed. So the state will move from here to here. And if both inputs are 1, both input bits here are, both registers contain 1, then at the end, the first register will continue to have 1. The second register will be turned into a 0. So you will get into the state 1, 0. Okay. Now I would just quickly, so maybe I should, so yeah, okay. So suppose the input was this, yeah, 0 plus 1 and 0. Well, how should you read this? Yeah, first of all, this means 0, 0 plus 1, 0. So the state vector in its, out of the 4 components, only 2 components exist, 0, 0 state and 1, 0. And each of them with equal amplitude, that is 1 over square root. Okay. So what happens if the input is this? Well, in the case 0, 0, nothing will happen. In the case 1, 0, this bit will be inverted to 1. And then there are, I will let you think about these things. I'm slightly running out of time, so I'll just move on. Okay. So, but yeah. So the other thing that we need to know is that when, so there's, okay, so what have I told you? State vectors, evolution. Evolution has to be done in a way that the length of the vector is preserved. Now, the only operations I have told you about are Hadamard and C0, and those preserve the length of the vector. So don't worry about it. What other complicated quantum operations can be done are not important to us. The only operations we will be using are the Hadamard and this control NOT. Okay. Yeah. So,
Jaikumar,
question. Yes.
There is a question.
Yeah, please go ahead.
So Petam asks why quantum gates are reversible, whereas classical gates don't have to be.
Yeah. So actually, I mean, now it depends on how fundamentalist you are. Okay. So there are people who would take the view that even classical gates, or at least the classical computers, are reversible, but those other parts of the output have evaporated in heat and noise, etc. Fundamentally, everything is fully quantum. Okay. So that is one point of view that you can carry. It so turns out that in classical computing, the way we have, our technology has evolved, certain aspects, or at least the way we are using, say, voltages, etc., to model computation, you can set things up so that the input is forgotten. But when you make things really small and go to photon level, etc., your operations have to be reversible. That is what quantum mechanics tells us. But as I said, classical is also reversible if you use Toffoli gates instead of your AND OR gates. So let me not tell you so much about measurements. We will barely need measurements. Okay. So, but the point is that when you measure a state, so just like a coin toss, suppose somebody says that this is this register contains a random coin. Yeah? And what do you say? What is its probability of being 0? It says it is P0. And what's the probability of it being 1? They say it is P1. But then you open the register and see it. Now, the so-called conditional probability of it being 0 is 1. You have seen it to be 1, seen it to be 0. Yeah. So this measurement is as if you have opened the register and seen and destroyed the uncertainty. There are some subtleties about quantum, what this is called is superposition, quantum superposition versus probability distribution. I mean, this is a very introductory talk. Let us not get into confusion. It's okay for you to incorrectly believe that it is the same thing. Okay, it's all right for today. Yeah, good. So let me just move on. Yeah. So, yeah. So now imagine that the quantum state, there are two registers A and B, and they are in state 0, 0, and 1, 1. Now, what does this mean? This means that somebody tossed a coin and they copied the information from register A to register B. So they put a random, they applied a dollar gate to register A, it got a random bit, and then they just copied it to register B, okay, using some classical operation. Don't worry about what circuit leads to this. Okay. Then what will be the resulting state of the two register system? If the first register is 0, since it was copied, the second register will also be in 0. And if the first register is in 1, then the second register will also be in 1. Okay. So we can say, using our fake quantum notation, which we use for classical, that the state of these classical registers is 0, 0 plus 1, 1. You might say they are correlated. They have become correlated. But in this state, if somebody asks you, what is the state of the first register? Now, how does one think about this in probability? You say, oh, what you want to know. I mean, that's the point. There is an English question. Okay. What is the state of the first register? And immediately the mathematician says, oh, you are asking about the conditional probability of the first register. Now, there is a little bit of a leap here, but let us accept that. So what is the conditional probability of the first register? Well, whether it was in this state, the conditional probability of the first, conditional probability distribution of the first register is 0 with probability half and 1 with probability half. And the conditional probability distribution of the second register is 0 with probability half and 1 with probability half. And there is nothing wrong in thinking about it like this in the classical case. Now, a very similar quantum state is here. It is in this state, 0, 0 plus 1, 1. This is called an entangled state. That's why the word entangled comes. We don't need to know much about that. But we could ask the same question. And if you were like me 30 years ago, just since I work with analogy, I would have said, oh, this worked in classical, it should work in quantum. The state of this register must be 0 plus 1 over. I'm sorry, huh? Yeah, I should have put a root 2 just to normalize. Yeah, my mistake. But I would have thought that the state of the first register is 0 plus 1 by root 2, because that's the way I've been misleading you so far. Okay. Now it turns out it does not work. Okay. For example, if you take this state, apply the Hadamard gate to the first register and measure, you don't get 0 and 1 with probability half. Sorry, you get 0 and 1 with probability half. Yeah. But in this state, if you apply the Hadamard and measure, you get 0 with probability 1. Yeah. So when do you say two states are the same? I mean, philosophers might have a reason to call two states same and different. We are a very pragmatic thing. If you do the same operation, you should get the same results. If applying a certain operation to the first qubit in this gives an observation or sort of outputs which doesn't match with this, we have no right to call the state of the first register when the combined state is this as this state. Okay, so that is all I wanted to say. And what? Okay. So now, yeah, so I have 5 minutes, and I will now here's the problem. Okay, again, classical problem. So we are essentially in the second part of the talk. Yeah. So there are two parties, Alice and Bob. Sorry, should I pause a little bit for the questions? So so I have said a lot of things, but yeah, don't take everything seriously. So I've tried to compare classical and quantum. Now, here's a problem which arises in classical cryptography. This has been there from the 19th century and even before. Yeah. And there's a standard solution to this problem. And I would like to describe that standard solution and then tell you what the quantum version of that solution is. Okay. And that quantum version has a name, and it's very mysterious, and it's very celebrated, etc. But let's try to see if we can come to terms with that quantum solution through the classical route. Okay. So what is the problem? There are two parties, and Alice has received a secret X, and she wants to transmit that secret to Bob by sending a message. Okay. A person seeing the message should not be able to determine what this bit was. Now, all this should not be able to determine, etc. What we mean is, no matter what circuit he applies to the message M, the output of that circuit will match with the actual value of this bit with probability at most half. That is what we mean by secrecy. Secrecy means after seeing the message, it should just look like, yeah, it doesn't help me in knowing what is there in X. Yeah. And there is a solution which, works in this case. And here is what we do. So you remember this state? This was the state we just described a little bit earlier, where Alice applies a dollar gate and copies the information over. So Alice and Bob, in advance, before Alice even has the information X, in advance they meet and they toss a coin. They both note it down in secret and put it in their wallet, yeah, and walk away. Now Alice is somewhere, Bob is somewhere else, and Alice has received this message X, or this information X, which she wants to send to Bob. What does she do? She does an XOR, yeah, just adds those two bits modulo 2. Yeah? So 0 plus 0 is 0, but 1 plus 1 is also 0. 0 plus 1 is 1, 1 plus 0 is 1. Okay. She adds this and sends it off to Bob. Now this message, if anybody looks at this message, do they have any idea what X is? Well, she has added this noise. So you should think of A and B as a noise. So what Alice and Bob do in advance is sit together and decide on the noise. They just toss a coin, create noise, and walk away. And this noise is added to the input. So this message is totally noisy. Yeah. And Bob then is able to cancel the noise, because adding the noise twice, modulo 2, will just cancel it. And Bob is able to recover this. Okay. All right. So this is how the classical one-time pad works. So what I'm going to do now is I'm going to unshare this and draw something on the board. So I have just a minute, but I hope I can take 2 or 3. Yeah. Yeah, is that okay? Yeah.
Yes, but
anyway, I should unshare in any case. Yeah. So
Jaikumar, there is a question.
Yeah, please.
I don't know whether
this is a good time. Yeah.
Okay. So Udit asks, shouldn't it be better if the probability was ideally exactly half? In at most half cases, if one observes 0, they could infer message to be 1, and that would be correct with more than half probability.
Say that again. So actually, if I say that he should be able to infer the answer at most half, in this case, it implies that it will be exactly half. I mean, you can, if you say that you can't do anything better than half, it means half you can always do. Yeah, because, okay, if you want to guess something with probability half, you just toss a coin and just, and you can never do it. I mean, if you say that you can't do it better than half, that means the answer is half. Okay. Yeah, maybe I didn't phrase it correctly in the slide, but that's what I meant. Yeah.
So Udit, if that answers your question, you can unmute yourself and ask.
it answers my question. Actually, I thought that sir had said that with at most high probability the person could succeed in intercepting the message.
Yeah.
So if I mean he could use the reverse logic then okay, that I am getting only this let's say I am getting 0 half of the times but less than half of the time, so he would infer that the message sent is 1.
Yeah.
That's what I was trying to say.
No, that is correct. But when I say that Bob should, the third party, the evil party is able to guess it with probability at most half, I'm saying the evil party as well as the complement of the evil party, which you just invented, both can do it with at most half. Okay. We don't know the behavior of the evil party, no matter which evil party you design. Yeah. They will be able to do it with at most half, which means by your logic itself, that neither of them can do it less than half either. If they did less than half, then the partner of that evil party who just does the opposite of the evil party, yeah, we would have done it in better than half. So yeah. Anyway, this is just a way of saying it mathematically in a succinct way, but don't worry. So now the question is this: can you see my board?
Yes.
You need to probably pin the screen.
Yeah. So everyone, they can click on Jaikumar's image, and on the top there is the 3 things. You can pin it, and that will allow you to see it bigger.
Yeah. So
Yeah.
I'm going to.
So there is another question, Jaikumar, but probably
Yeah,
you can take it after the.
Yeah, you decide. Yeah. Okay. So what I've done here is this is the same one-time pad drawn as a circuit. So at least we become familiar with quantum circuits. Yeah. So what happened? Initially, Alice tosses a coin. Alice tosses a coin means she applies the dollar gate to her register. Then she copies the information to Bob. So let us say Bob starts with the value 0. So to copy the information means she adds her input to this. So if this was 0, this will say 0. If this was 1, this will stay. So now if you look at the state of these 2 registers, ignore this for the moment. With probability half, it is in the state 0, 0. With probability half, it is in the states 1, 1. Okay, which was what we. So this is how you create this state. Yeah. Now, Alice has received some state X. We don't know what this state is. Alice also doesn't know. It is kept inside a little box, and it happens to be the state which has probability P of being 0 and Q of being 1. Yeah? It is this. And she would like Bob to possess this state. That is the register B to get this state. Yeah? That is what it means to transmit from Alice to Bob. Okay? This is how we are modeling. Okay? So what was the first thing she does? She takes the sum of these 2. Okay? So she has computed the sum. That is, taken this and inverted this if this is 1, which is the same thing as computing the XOR of these 2. So right now what happens? This is still what it was, except it has got correlated with this in some funny way. Yeah? And then this message goes to Bob, and Bob uses this to adds it to his register, and somehow the output is correct. Yeah, I mean, if you believe the one, somehow when I wrote the code for the one-time pad, it looked very convincing. And the moment I draw this circuit, it starts looking a little strange. So let us just understand what will be the state at the end. Okay. So I will not work you through it. If you just ask systematically, what was the state here? What was the state here? What was the state here? What you will realize is that at the end, if this is 0, this will become 0. And this was 0 with what probability? P. So in the end, these 2 registers will be in the state 0, 0, and they will be in the state 1, 1 with probability Q and probability P. And this register, which is what the evil party has seen. Yeah, the evil party has seen, just looks random. It has, with no matter what happens here, this is half with probability, 1, 0 with probability half, and 1 with probability. It has gone, what they say, it is in tensor. It has got, it is independent in probability language. it has become independent of what is happening in these two registers. Okay. Now, everything that I have written here looks like a quantum gate, except this. Yeah. So if I have changed this to a Hadamard gate, which I insist is the and now, by analogy, what should happen? Yeah. I mean, if it worked last time, it should still work. The p's should turn to alpha. These double brackets should become single brackets. I mean, why not? Yeah, I mean, there is no reason why this should not happen. It is the same circuit. I have changed nothing. The state was the same here, and exactly the same operations are happening. I mean, physicists have this reason to use amplitudes instead of probabilities. But that should not make a difference. In the end, I should get the same. Okay. Now, the question is, has Alice succeeded in transmitting her quantum state to Bob? Yeah. The answer is no, because I said that in this state, if you look at the value of the second register, it is not the same. Yeah. In classical, this was enough. In quantum, this is not enough. Okay. So imagine now. So let us do a classical experiment. That is, Alice had a one-time pad. She used the one-time pad to transmit the information to Bob, but she was paranoid because there is going to be an income tax raid at her house, and she still has X with her. And what if somebody finds out this X? It will be a disaster. Yeah. So what can she do? She can say, oh, I'm going to erase this X, and what better way of erasing it than putting a dollar gate? I just destroy my information. Okay. Now you might say, why didn't she make 0? That's because that 0 won't help me in the quantum, so I'm going to put a dollar gate. Okay. Now, if you believe this, this is how one forgets information. Yeah, by putting a random bit there. Why not put in quantum the Hadamard gate? So if you put the Hadamard gate here and then ask, what is the state of these two registers? This register has gone in tensor, and you just look at this register. It will turn out that you will get 0. Don't worry about these normalizations. So trust me, if you apply this Hadamard gate and rearrange, this 0 will become 0 plus 1 by root 2. This 1 will become 0 minus 1 by root 2. You rearrange this and you get this. And suppose Alice were to measure this, she will find 0 with probability half. And when she finds 0, Bob has got the state that she wanted. And if she gets a 1, Bob has got this state, which is not quite what she wanted. She wanted it to be alpha 0 plus beta 1. Yeah. So she tells Bob, please apply this matrix if I have a 1, change the sign of this from negative to positive. If I don't have a 1, if I have a 0, be satisfied with what you have. Okay? Now this bit has become deterministic, which is either 0 or 1 because we have measured it. And this register has magically become this. Okay? Yeah. It turns out that you could also have done a measurement here, yeah, and a measurement here. And then what the result of that is this state has jumped from this register to this register. Now, I'm gone way over time. So this is what I wanted to tell you, that there is a way of understanding quantum teleportation from the way we do secret communication using the one-time pad. Okay, and if you try to do every randomized computation underlying this one-time pad using fake quantum notation, then it might give you some comfort with how the calculations for the teleportation play out. So I'll stop here. Yeah, I realize that things are probably not 100% clear, but if you go over the talk again and look at other resources on the net, I hope what I have said today adds something to what is already there. Okay. So I'll stop here. Thank you very much for your patience. Any questions? Yeah, feel free. I have time. So yeah, so if you have a question, if you want me to explain something here more carefully, I can do that, or some general questions.
Thank you very much, Jaikumar. I think it was really helpful, not just for physics people, but even for us. There are definitely already questions. I will first ask Govind to ask his question, and then we can. Govind, if you are there, could you please unmute and ask your question?
Hello.
Yes, please. Yes.
Sir, how does classical gates in quantum, if classical gates are reversible gates,
Yes.
let's suppose if I make 2 cross 2 classical gate, then can I use in quantum domain? And if it is used in quantum domain, if not, then what are the parameters that affect these classical gates not to be used in quantum domain? Also, I have other question that you said that Toffoli gate is faster than classical gates.
No, I didn't mean to. Yeah, go ahead. Yeah.
So how does these Toffoli gate, I mean C0 gates are faster, that quantum gates are faster than the classical gate, as it is made up of the universal classical gates?
Yeah. So first thing is, what sort of classical gates can you use? As long as it is reversible, you can use it. Yeah, because every reversible computation can be written down again using Toffoli gates. So if we assume, so we will say that our model for quantum computation involves only one gate. It turns out, because of how transistors evolved, etc., and how logic evolved in mathematics, that and, or, and not have become very important operations. Okay, it might well be that another civilization, it talks only in terms of Toffoli. Okay, so just Toffoli gates are enough to compute it. I did not mean to say that Toffoli gates are faster than and, or, and not. To realize the same computation, you might need a certain number of Toffoli gates. But the same computation often can be realized using fewer quantum gates. And which sort of quantum gates? The kind of this sort of quantum gate. This is actually a classical gate as far as I'm concerned. Okay. Yeah. This has this funny behavior that when you feed it 0 minus 1 by root 2, it produces a 1. And if you feed it 0 plus 1 by root 2, it produces a 0. Okay, so there are two kinds of superpositions possible, and Hadamard gate helps me distinguish between those two superpositions of 0 and 1. Okay. By using gates like this, you can do certain operations that we are not able to do classically using the same number of gates. Okay, I don't allow you to use Hadamard gates. Use as many Toffolis as you want. There are problems where you will use very small number of Hadamard gates and you will need exponentially many Toffoli gates to do the same thing.
Thank you, sir.
Are there any other questions? Please, you can ask on the chat window or you can unmute yourself and ask.
Yeah. So, sir, you have explained this Hadamard gate, and
Yes.
as per I understood that this is the basic gates in quantum computation. Okay, equivalent to the NOT gate in electronics transistor. Okay. So, what would the physical realization of these type of the gate?
Yeah, so I'm not the right person, but I think we are very close to the answer. So let me just explain. Yeah. So the question is, what is the physical realization of this? So one could need, the first question even before that to answer is, what is the physical realization of the qubit itself? Yeah, because for example, in classical, we said our people could have asked, bits are there. Logicians were working in the 18th century, maybe in India, there is Jain logic from 2000 years ago. Yeah, so I mean, notion of a bit, let us say, is understood. It should be 0 or 1. But a physicist might come and say, what is the realization of a bit? So maybe at some point they said, oh, any voltage below 0.5, we will call 0. Any voltage, okay, so maybe above 4, we will call 1. Okay, so our realization of a bit is voltage. Below 0 is 1, below 0.5 is 1, above something is 1, and we will promise you that nothing in the middle will ever appear. Okay, good. So that could be a realization. And then you can say, how do I make a 0 into a 1 and 1 into a 0, and how can I implement the AND operation, and you design various kinds of transistors with some semiconductor properties so that when two are high, then the output becomes high, but if only one of them is high, the output doesn't become high. And that becomes, that's called an AND gate somehow. Okay, yeah. So now the question is, what is a qubit? Yeah. So you could say a qubit is, you can call it the polarization of a photon. Okay. So it turns out that photons have polarization, and you can say if it is horizontally polarized, I will call it 0. If whatever, and if it's polarized in another way, then it is 1. One of them is 0, the other is 1. Now, if you pass this photon, which is horizontally polarized, through a crystal, yeah, it goes into a state which is a superposition of the two of them. Okay, let's say 0 plus 1 by root 2. But the same crystal, when fed the other kind of polarization, also produces a superposition of 0 and 1, but with a minus sign. So if you were willing to do computation using photons and crystals, I'm not a physicist, I'm far away from anything experimental, but I can imagine that if you believe this is how quantum mechanics works, then by putting crystals where I have got gates, you will be able to realize, and you had detectors to do the measurement in the end, with a small number of crystals in this, I will be able to realize a certain computation which I care about. Okay. So now I don't know that much about practical quantum computing. So there are these things called superconducting qubits, and there are other things where you use the spins, various things to realize quantum effects. But that is how you realize quantum circuits in practice. The point is that we are still far from anything useful. Yeah.
So we have Anand. Would you like to add something? Like, he is someone, and there are many other people in the audience.
Yeah, please, experts say.
So
yeah.
No, I think I mean, this is the best explanation, I think, even as an experimentalist. So yeah, photons are the one way, but I think for actual computation, photons may not be the best candidate. They're probably good for communication from point A to point B. But for actual computation device, maybe superconducting qubits, semiconductor, the other candidates that actually, yeah, but the polarization of photon, that's probably the best platform to kind of explain what a qubit is and how a gate can be explained.
Yeah. So if you want to convince yourself that about the plausibility of quantum computing, photons are good. But if you want to build a technology, there are others. Photons don't you can't hold them for very long. Yeah.
Are there any other questions? Please feel free.
Yeah, so thank you for this opportunity to speak
Well,
on the same topic.
Yeah,
20 years later.
I think
Pleasure.
at least clap from wherever we are. This is a fantastic job. Thank you so much.
Yeah.
Thank you.
Thank you for calling.
Thank you very much.
Yes. Yeah, I realized that this was the first lecture, and
it was a great lecture. Thank you.
Okay, so yeah.
Anand,
Okay, I hope to see all of you sometime, and so until then, please be safe. Take all precautions. I hope this goes away soon, and we can do things as we used to. At least the good things we used to.
Thanks. So Anand, there is a question for you, I guess. You can probably say that how to join the series, lecture series.
Okay.
Email you or something.
Yeah. So well, first of all, Harsha says amazing talk. So since he didn't,
beyond it.
Thank you very much. Thank you.
So this quantum information and coherence, this is going to be a series. We'll do at least maybe about 2 talks a month. So that will be covering physics and computer science aspect, the different aspects of quantum information in general. That's why we call it quantum information and coherence talk. Information for the computation part, coherence for the physics part mostly. So yeah, so we'll be doing about 2 talks a month. We'll see how far it goes, but yeah, that's the plan for now.
So Anand, yeah, probably if someone wants to join the mailing list, he can email you. Or?
Yeah. If you want to be on the mailing list, just drop me an email. That's it.
Okay, great. Okay. Thanks, Jaikumar. I'll finish the talk.
Yeah. Thank you very much.
Thank you. Bye.
I'll leave.